Hey everyone, I'm Jamie, and I've been coding for over 20 years, and this series proves you don't have to be perfect to build something cool. We're creating a simple, data driven 2D game engine and editor, step by step. The idea here isn't speed or polish, it's clarity. Every line we write should make sense before we make it fancy. So grab a coffee, sit back, and let's keep building this thing, one solid piece at a time.
Spreading knowledge, one byte at a time.
Alright, welcome back. Last episode, we got our workspace structure in place, engine, renderer, editor, and proved that the BHVR setup, Bun, Hono, V, React, wasn't just a theory. We had a square on the screen moving left to right, driven by our renderer and engine loop working together. Today, we're taking the next step in that foundation by adding our own @GES/ECS package. This is our entity component system, the part that lets the engine think in terms of what things are instead of what things do. It's how we'll separate data from behavior, and it's the core of how almost every modern engine organizes game logic. Now this version is super bare bones. We're not optimizing, we're not caching, and we're not chasing performance numbers. We're building something clear and educational so we can reason about it later when it's time to optimize. I want you to see the entire loop. Entities exist, components describe them, and systems act on them each frame. Our world class will let us create entities, register components, and those components to entities, and query for sets of entities that have specific combinations of components. That's the heart of an ECS. A system can say, give me everything that has a transform component and a velocity component, and the engine will hand back just those. To keep things simple, we'll use three components: transform with an X and Y, velocity with Vx and Vy, and shape with a width, height, and a color. We'll create three systems: a movement system that updates position based on velocity, and a shape render system that tells the renderer how to draw it, and a bounce system, a system that will keep the square within the screen. All of that will plug into our existing engine update, which will run each tick, and our existing render, which will run each frame. By the end of this video, visually nothing really will change. We'll still be seeing the same square drifting across the screen, but under the hood, it is no longer hard-coded logic in a loop. It's an actual engine executing a system that's reading and writing component data. That's a huge shift in architecture, even if the screen looks identical. The goal is to get a good mental model of how these pieces fit together before we start making them faster or smarter. Once we have an engine, renderer, and ECS talking clearly, we can start adding those tools to the editor and modify live component data and see immediate feedback. That's when this setup starts to feel real. So think of today as laying the tracks. The train isn't running at full speed yet, but when it does, everything will already be pointed in the right direction. Alright, let's get into VS Code and build our @GES/ECS package. Alright, so we're back in the project here. We're going to go into our packages, and we're going to do the same thing as we have been. We're going to go to, in this case, engine, and I'm just going to copy that. I'm going to rename it to ECS. We're going to go into ECS and change our name in the package to ECS here. Let's change this to ECS, and this will just be entity component system. We'll tell it that it's in the ECS folder inside of the GitHub repo there. And that's all we really need to do here. We're going to go into types and source or an index here, and we're just going to get rid of everything. I'm going to start by doing our export asterisk from types. I'm also just going to start by creating the world class, just initializing it, because we're going to go into types and we're going to start filling this out here. So first thing we will need, because we're going to use it, is that world. I'm making an entity a simple number, literally a numeric ID. Why? Because an entity by itself doesn't do anything. It doesn't store anything. It's just a unique handle we use to attach data. Think of it like a coat hook on a wall. The hook on its own isn't very interesting. The magic happens when you hang different coats on it. In ECS land, those coats are components. The big win here is that a number is trivial to copy, compare, and pass around. It keeps overhead low, and it keeps our mental models simple. Now, components. A component is just a small bag of data that describes a single aspect of an entity. Position, velocity, health, color. Those are all great component examples. To describe the shape of a component, I'm creating a component schema interface. I'm deliberately keeping it loose right now. It says any set of keys with any type. Why would we do that, especially in TypeScript? Because in the foundation phase, our priority is to build the habits and the seams, getting the data in the right place and getting the flow correct. Later on, when we introduce a component registry, we can tighten this into strict schemas per component name and get full IntelliSense for free. For now, flexibility is forgiving, so we can move. Component instance with the T answers the question, what does the stored data for a component look like? If I say my transform component is X number, Y number, then a component instance of type transform is literally that object. You can think of component schema as the idea of the shape and a component instance as the concrete value that lives on that specific entity. I'm defaulting T to the component schema so that if you pass anything, it's still flexible. Component map is where the rubber meets the road for storage. For a single component type, for example, transform, I want a fast way to answer two questions. Does Entity 42 have this component? And if yes, please give me its data. A JavaScript map keyed by entity IDs is perfect for this. O of 1 lookups, simple semantics, and we get to keep TypeScript's knowledge of the value shape, so component map is basically a map with entity as the key, component instance as the value. That's all of the magic we need right now. The update, passing in world and delta time, gets called from the engine during the simulation phase. The world parameter gives the system access to entities and components via the query API we'll be writing in a moment. The DT, delta time, is the amount of simulated time to advance. Update system should do frame rate independent math. In practice, you'll see me write things like position plus equals velocity times dt. This is a render system which won't depend on delta time. Render, passing in world, gets called during the presentation phase. Notice there's no dt here. That's intentional. Render systems should read the current state and tell the renderer what to draw. Rectangle, sprite, text, whatever you like, without advancing time. If the render system needs a clock for effects, it can read it from elsewhere. But the contract says crystal clear, update is not equal to render. All right, now we're back inside of the main index here. I'm going to create entity IDs by counting upwards from 1. I'm not recycling IDs yet. That would add complexity we don't need while the mental model is forming. If we ever need to recycle, we can add a simple free list later on without changing the public API. Here's our component registry. It's a 2-level map from component name like transform to the component map for that type, which itself maps entities to component data. This layout keeps reads cheap and the code easy to reason about. I'm maintaining 2 lists of systems. Update systems, run during simulation and always get the DT. Render systems run during presentation and never get the delta time. Right now, execution order is simply the order in which you add systems, which makes behavior predictable while we're learning. We can add prioritization or phases later. Create entity is the world's hand me a new coat hook function. I return the current counter value, then bump the counter. On its own, entity has no data. It becomes meaningful as we attach components. Before we attach a particular component type, we register that type by name. Registering allocates the map for that family and also gives us a place to validate usage. If we later try to add a component to a type that wasn't registered, we can throw an error loudly and immediately, which helps catch typos and wiring mistakes while the code is still fresh. Add entity, passing an entity, type, and props, attaches a concrete component instance to a specific entity under the hood. I grab the map for that type and store props under the entity ID. If that type hasn't been registered, I throw an error on purpose. Get component, entity, and type is the just give me that one thing helper. If the entity has that component, I return the data. If not, you get undefined. I let the caller mention the expected shape via the generic, so TypeScript can help with the property names on the other side. Query is how the system asks the world for all entities that have these components. I'm going to implement it in small steps. The important idea is that I'm returning a generator, which lets me stream results one at a time. That means I don't have to build a giant array first. I can yield a result as soon as I find it, and the caller can break early when it's satisfied. Each line in this method ties directly to this logic. This is a quick guard. If you ask for nothing, I give you nothing. Subtle UX choice here. I could throw, but a silent co-op keeps call sites tidy when a system builds its filter list dynamically and sometimes ends up empty. So we sort the requested component types by however many entities have them, smallest first. Why? We iterate the base set and probe the rest. So starting with the smallest or rarest component minimizes wasted checks. Mathematically, it's still about the base set size times however many other components we're checking, but in real life, this is a massive speed up because the base set, the smallest one, is usually tiny compared to the rest once we've sorted it. So we pick the rarest type as the driver for our scan. If it isn't registered, or no entities have it yet, can bail instantly. That's a fast path to no matches without allocating anything. Alright, this is stream mode. This is why query is a generator. We walk each candidate entity once and only build enough data to decide if it qualifies. The caller can break as soon as they're satisfied, so we seed our result payload with the base component's data. The shape we're yielding is an array with entity as the first element and an object with the type name and component data as the second. So we probe the rest, constant time hash lookups per component type. The first missing component short circuits the check. No need to keep looking once we know the entity won't match. And here's the payoff. Yield as soon as we confirm a match. No big intermediate arrays, no sorting the results, just a clean stream of entities and a bag of components. On the consuming side, you could write something like, and then you could break whenever you're done. Add system with system and options registers either an update or a render system. If you pass a phase render or phase update, I'll respect that. If you omit it, I infer the lane using instance of, because these are classes, not just TypeScript interfaces. Index of works at runtime. This keeps call sites tidy without sacrificing clarity. Update, passing in DT, runs a simulation pass. I call each update system in the order they were added and pass along this instance of the world and delta time so they can do time-based math, movement, timers, AI. This is their home. Render runs the presentation pass. I'll call each render system with the world so it can read whatever components it needs and issue draw calls to the renderer. No delta time shows up here. We keep render stateless with respect to simulation. Next, we're going to go into core and we're going to update the package. We're going to add the ECS file. So we're exporting ECS from both the ECS file and from the index, just like we do the rest of the systems. Now, we do need to make sure that we add it as a dependency. And it looks like we need to edit these two. It must have gotten messed up while I was working. All right, now we need to build and install. Looks like the core failed. Can't forget to save. All right, now it's time to go into the client. Let's do something different here. We're going to create a new hook. This will let us, we'll call it useGame. And this hook will kind of set up the entire thing and allow us to use that in the editor component. So it'll set up the world, it'll set up the components, and it will get the simulation running. So let's build that first. So we'll come into our source, we'll add a new folder called hooks, and then we'll add a new file. We'll call it useGame.ts. So we will import use effect, use ref, use state from React. Then we'll import make canvas renderer and renderer from @ges/core/renderer. Then we'll import our engine and renders or engine and type engine props from @ges/core/engine. And then finally, we'll import our world, our render system, and update system. So the useGame hook encapsulates all the engine setup logic in one place. I'm accepting a canvas ref from the component and returning an add square function so the UI can spawn squares dynamically. This keeps the component clean and makes the game engine specific logic reusable. The transform component holds the entity's position in 2D space. By keeping this separate from the shape and velocity, we enable flexibility. Some entities might have position, but no velocity, a static object, or velocity but no visual representation, an invisible force. The shape component describes an entity's visual properties. This component is purely about presentation, width, height, and color. By separating this from transform and velocity, we can easily have entities that share the same shape but different positions or speeds. The velocity component stores how fast an entity moves per second along each axis. Vx is horizontal speed. Positive is right, negative is left, and Vy is vertical speed, positive down, negative up. The movement system will read this and modify transform accordingly. The square interface is our aggregate type for creating entities. It bundles transform velocity and shape together so the UI can pass along the data at once. Under the hood, we split this into separate ECS components, but this interface keeps the public API simple. I'm using refs to hold the world, renderer, and engine instances. These need to persist across renders, but shouldn't trigger re-renders when they change. That's exactly what refs are for. The FPS state does trigger re-render because it drives the UI display. Here's an early bail. If the canvas isn't mounted yet, there's nothing to do. React will call this effect again once the ref is attached. We need the parent element to size the canvas properly. If it doesn't exist, unusual but possible, bail early to avoid errors downstream. Make Canvas Renderer passing in Canvas gives us a drawing API that wraps the canvas 2D context. I'll call resize immediately to match the parent's dimensions. This ensures that our coordinate space matches what the user sees. Storing it in a ref means systems can access it without triggering re-renders. Here's where I create the ECS World. I register 3 component types: transform for position, shape for the visual data, and velocity for the movement. Registration allocates storage maps for each type and enables the type checking. If we try to add an unregistered component later, we'll get an immediate error instead of a silent bug. Every frame, we clear the canvas to a dark background. This wipes the previous frame so we can draw a new one cleanly. World.query with shape and transform streams all entities that have both the shape component for rendering and the transform component for positioning. Now we're able to draw a square at the entity's transform position X and Y and its transform shape, width, height, and color. By putting an underscore here before entity, we tell TypeScript that we're not going to be using the entity within this function. The square render system is responsible for drawing all squares to the canvas. It extends render system, which means it runs during the render phase. No DT parameter, the separation keeps render stateless with respect to the simulation logic. I register the render system with the world, explicitly marking it as a render phase system. That ensures the runs during world render instead of during world update. The movement system runs during update phase, so it receives delta time in seconds. This lets us scale movement by an elapsed time, which keeps motion smooth even if the frame rate fluctuates. World.query with the transformer velocity gives us all the entities that move. For each one, we update the position based on its velocity, multiplied by the dt, ensures consistent speed. If velocity is 100 pixels per second and dt is 0.016 or 60 fps, then we move 1.6 pixels per frame. We register the movement system as an update phase system. It will run every simulation tick, 240 times per second by default, keeping motion smooth and frame rate independent. The bounce system handles collisions with the screen edge. It runs during update, but it doesn't need delta time. We name it underscore so it signals to ignore that. This system enforces boundary constraints and reverses velocity when entities hit the wall. We query for entities that have all three: transform, position, velocity for movement, and shape for size. We need shape because collision detection requires knowing the entity's width and height, not just the top left corner. This is a right wall check. If the entity's right edge, x plus width, exceeds the canvas's width, clamp it to the boundary and reverse horizontal velocity. Clamping prevents the entity from getting stuck outside of the visible area. This is a left wall check. If the entity's left edge, x position, goes negative, clamp it to 0 and reverse the horizontal speed. Multiplying by -1 flips the direction while preserving speed. This is the same thing, only obviously for the y velocity and y position. We register the bounce system as an update phase system. It runs after movement system. Systems execute in registration order. So position updates happen first, then boundary checks, so order matters. If we reverse it, entities would bounce 1 frame late. So during the render phase, we delegate the world's render systems, like the square render system. They live here, and keeps the update render separate and makes code easier to reason about and keeps presentation stateless. After rendering, we update the frames per second display. This triggers a React re-render of the UI component that shows the frame rate. Doing this in the render callback ensures the display stays fresh. So essentially, we're doing the same thing we did last time. We're creating our engine props, we're passing them into our new engine, but we are setting engine ref to the current engine there. So we start it, and then when the use effect returns, we clean it up by stopping the engine. All right, and then we are going to we're going to rerun this useEffect hook based on the canvas ref and when that changes. Now, here comes the cool part. After our useEffect hook, we can create a function that will add squares. So at the beginning of our add square function, we're going to set world to the current, the world ref.current. At the beginning of our add square, we'll set world to the world ref.current. If no world has been initialized yet, we throw a warning. One thing I'd like to change is we can destructure the square up here. So this function will check to see if the world has been initialized, and if so, it'll create a new entity. Then it will add that entity with each individual component, setting its value as well. Now, lastly, this is a hook, so we can return from this hook some relevant data. So we'll actually return that function add square and the current FPS. This way, we're able to use it whenever we require this hook. So it looks like FPS might not have been spelled correctly. Let's check FPS. Here we go. We need a few things that are wrong. Lastly, what we can do is go back into our editor component here. We can get rid of everything from here. And we can say const add square and FPS are equal to useGame, passing in the canvas ref. Then we can get rid of everything that we aren't using anymore. We are using useRef. Let's just for now create a button. So we'll say const, no, we'll just create the button. So under this, we'll put a gap of 4. And then under here, we'll create a button. Import from @components/UI/button. All right. Let's see what we have here. Bun run or bun dev. All right. So I'm getting an error right now that says transform is not registered. So transform. And we do have another error within the bounce system. All right. So now if I open this up, http://localhost:5173. We have a button says as square, We click it, and there is a square, and there's another one. Now we can start to kind of add some UI elements, and we'll be able to add a square with different parameters, but we'll leave that for a different day. All right, let's recap what we pulled off today. We built out our @GES/ECS package and new foundation for handling data and logic in a clean and modern way. We defined entities, components, and systems, and we wired them into our engine so that now every frame, instead of hard-coded logic, we're actually running systems that read and write component data. We've improved our architecture works by rendering the same moving square, just now powered by the ECS logic. It doesn't look very different, yet under the hood, it's a huge leap forward. Our engine is now structured, predictable, and ready for more features. In the next episode, we're going to start using the editor to actually interact with the game state. We'll build a simple UI on top of what we have, buttons and forms that will let us add new squares directly inside of the running game. So instead of editing data in code, we're actually updating our ECS world in real time. This is where the editor stops being just a viewer and starts becoming a tool. If you made it this far, nice work. We've got the engine ticking and the renderer drawing, and now our ECS is officially online. Next episode's when things get fun, seeing your UI directly control the game. If you're building along, drop a comment and show me what you've got working, or tell me what system you'd add next. And hey, if this episode helped, hit like, subscribe, or share it with a friend who's been meaning to finally build something from scratch. I'll see you in the next one.